Good day, I'm Dr. T, and welcome to my office. Today I'd like to talk a bit about light. Light affects how we understand our atoms, as well as our understanding of light itself influences how we understand how our atoms function, especially once you crack the hood on the atom and start looking beneath the metaphorical billiard ball. So to understand light, of course we've been thinking about this since there's been people thinking, but I want to jump back to the Enlightenment. Since the Enlightenment, especially individuals like Sir Isaac Newton, have been, systematically trying to understand light, and Newton developed the field of optics as well as calculus, really in his pursuit to understand light as well as motion and other things. Of course, things have progressed a bit since there, but Newton was faced with a bit of a challenge, as well as really everyone up through the early 20th century. And that is, light does some rather interesting things. Or I should say, light does a set of things that shouldn't be together. For starters, light behaves like a wave. This is actually the key to Newton's optics. When waves travel through different things, their speed changes, and depending on the shape of the thing they're traveling through and the amount of speed it has changed, you can change the direction of the wave. That's how my glasses work. The light traveling through them, because the glasses slow down the light a little bit more than the air does, actually probably a good deal more, then it's able to bend the light and make it hit the retinas of my eye a bit better because my eye is the wrong shape for my lenses. And hey, we've got optics, and of course we have, different colors, and we get, those are different properties of waves. Changing how the type of wave. It's traveling at the same speed, but it's a little bit longer wave, a little bit shorter wave kind of thing. Okay, so light's a wave. But remember how I said there were properties that didn't go together? Because light also has properties of particles. And one of the key properties is one of the more obvious ones. Shadows. See, particles are the ones that leave shadows. If you imagine spray painting something and there's something in between your spray can and the thing you're painting, you'll see it. The paint droplets won't hit what you're painting. This is a shadow. If you watch the crime shows, you'll usually have the one scene where, the detective walks in, does something cool with his glasses, which of course I'm not cool, so that didn't look cool, but, they get an actor who can do something cool with their glasses, and they look at the blood everywhere, depending on what network it is. Maybe it's just a little bit of blood for the more family-friendly networks. But there's no blood over in that corner. And like, there was a second killer. Da-dum! Yeah, so light does this, and that's totally a particle thing. And that left a bit of a question. Which is it? Is it a wave, or is it a particle? Because it can't be both. Or can it? And so individuals like Max Planck started noticing in the late 19th century, early 20th, that light was doing a lot of other really weird things. For starters, it was behaving in a rather interesting way. It was as if the light wasn't a continuous amount of energy. In theory, you should be able to subdivide energy infinitely and make smaller and smaller parts of energy, but you can't. At a certain point, you have energy coming as little packets, apparently, or quanta, small amounts that aren't subdividable. There were some rather interesting experiments that were doing some odd stuff, where you would shine light, and the brighter the light got didn't necessarily mean it behaved like more energy was coming off of it. This was weird. And this was a problem that, was going to take an Einstein to figure out. Albert, to be precise. Albert Einstein, in one of his key papers, figures out or starts proposing the idea, and he was, by the way, not alone at this. But he was the one that really started laying the groundwork that light really was both a wave and a particle at the same time. An idea that would become coined as a photon. So the idea of a photon is that it is a packet of light. The light itself is a wave. Unlike other waves, it doesn't travel through something. It doesn't need a medium. Other waves do require something to travel through. Sound waves require air. Ocean waves require, an ocean. But light doesn't need that. It's a special case here. And these waves are themselves little packets. So it's both a wave and a particle. And if you're thinking this sounds weird, welcome to where we're going with this. This was one of those categories where, it seemed a little bit weird when things started, and it just keeps getting weirder. Remember how I mentioned that light was in these small particles, these kind of quanta? This is where we start getting the terms quantum or quantum physics, which of course as chemists we're going to be applying. The classical world, the world of Newton and of logic and really what you're used to, a lot of the rules don't exactly apply, and quantum physics gets a tad bit on the weird side. But with that said, it is a thing, so we're going to try and get a basic understanding of what's going on. But don't feel bad if it all seems kind of weird. That's only because it is. So to understand light, it's helpful to understand more classical waves. So like waves in the ocean or sound or whatnot. And we're actually going to look more at the kind of ocean style. That's what we call a transverse wave, one where the particles go up and down and you get your nice wave. And not really the longitudinal wave like sound, which goes, like this. What I'm talking about does apply to the longitudinal waves, but they're a little bit harder to understand, and light is a transverse wave, so let's look at transverse waves. So transverse waves, of course, you get that nice waving look. Editing will have a thing up here with the wave. Okay, so we got 4 key properties to the wave. The first is going to be amplitude, usually abbreviated with an A, and that's the difference in the height of your peaks. There's a couple of versions of amplitude, but the key thing to keep in mind is, how tall are the peaks. Generally speaking, this is where the energy is lying in everything except for light. Amplitude doesn't really apply to light per se. Amplitude, when it comes to light, is actually the number of photons. And if you were to then think of this as a wave, the higher the peaks just represent more and more photons. For, say, an ocean wave, it is literally the height of the peak. And if you're listening to, say, the shipping forecast or your marine weather forecast, they'll tell you how high the waves are because, a big enough wave, bad things to the boat. But we've got ourselves amplitude. As chemists, we generally ignore this. For most of what we're doing, the number of photons might be relevant, but it's kind of on the back burner kind of thing. It's either going to be all about the number of photons or all not about it. Okay, next property is speed. And for light, this is going to be fixed at about 3 times 10 to the 8th meters per second, a smidgen less, and is abbreviated with a lowercase c. Now, this is in a vacuum. As I mentioned in the first part of the video, light changes speed depending on what's going through. So once again, we're going to be dealing with in a vacuum, and we're going to be making a lot of assumptions when talking about quantum physics that are not exactly valid, but they're good enough for what we're doing. Okay, the next 2 properties are the ones we tend to look at the most, and they're connected with each other, so it's kind of an interesting feature. First is wavelength. This is the distance between any 2 light parts of the wave. So you can imagine the top of the peaks, or the 2/3 of the way down, traveling to 2/3 of the way down. Just pick a spot on the wave. This is given the Greek letter lambda. Kind of looks like an upside down Y, even though it's not. And it's measured in a length unit. For light, you're probably looking at nanometers, or if you're going more of the, not necessarily SI, angstrom, which is 10 nanometers. The other one is going to be frequency. This is given the Greek letter nu. It looks like a squiggly V. It really looks like a V. It's not a V. It's a nu. And this is going to be how often the wave interacts or goes up and down per unit of time. So pick a location as the waves are going, it's when it comes back to where it was. So, and 1 wave, 2 wave, that kind of scenario. That's going to be measured in a unit called hertz. A hertz is literally 1 divided by seconds. So it's an inverse second. Of course, light is going to have fairly high frequencies, to say the least. Now, the speed of a wave, whether it be light or anything else, is going to be equal to its wavelength multiplied by its frequency. Remember, speed is going to be given in length units divided by seconds, and hey, length is in length units, and frequency is in 1 over seconds. So, yay. Okay. Now, with light, once again, it's a bit of a special case. Most waves, we talk about the energy of the wave as a whole as its amplitude. Light has two energy functions. First is just how many photons do you have? Really what we would call amplitude. But quite often, the energy of the whole is less important than the energy of an individual photon, because that's what's going to be interacting with atoms. Atoms interact with one photon at a time.
Hey, this is me from the future. So I thought I should point out why we actually care about energies. So atoms and molecules, for the most part, can only interact with photons if they can take the energy from the photon and store it very, very briefly. Now, they only have certain amounts of energy they can store, so if the energy is a little too high or a little too low, then for the most part, the photon is simply going to go past the atom and have no interaction with it. So for instance, the molecules in our eyes that allow us to see have a fairly narrow range of energies that they're able to store, and thus we can only see a very narrow range of the spectrum. The cones in our eyes, which see color, have an even narrower range, and that actually allows us to see color because our brain knows which cones see which range. So if it's on the kind of the high side, it knows it's okay, only the blue cones are accepting it, and therefore this thing is, blue. If it's a little bit on the lower end of what we're able to see, then hey, that's only the red cones that are going to be taking it, and your brain knows to put some red in there. Back to the video.
Now, for the energy of a photon, we're going to be looking at Planck's constant, which I will put somewhere, I don't know where, but somewhere on here, times the frequency. In theory, you could do this with the wavelength, but the units of Planck's constant are such that we do it with the frequency. Obviously, you can interchange frequency and wavelength if you need to by doing a little bit of algebra. Now, you could multiply the number of photons by Planck's constant by the frequency to get the total amount of energy, but usually you just care about the energy per photon, so that's not usually something you do a lot. With that said, have a wonderful day, and we will jump into the atom in other videos.